Hello everyone. So our topic today is on the turbulent flow of viscoelastic fluids. We look at the polymer-induced drag reduction phenomena in turbulent flows. So my name is Li Xi. I'm from the McMaster University and from Canada. And the work was done by a former PhD student, Lu Zhu. Let me start with a very quick introduction. We all know about the polymer drag reduction phenomena, which basically says that if you have a very low amount of polymer additives, which we are talking about 10 to 100 parts per million, and you add them into the solvent, and you can significantly reduce the friction drag of a turbulent flow, and the reduction can be up to 80% in certain cases. That means for the same pressure gradient, for the same driving force for flow, the flow rate you get from dilute polymer solution can be much higher than that of a Newtonian turbulent flow. Obviously, this is an important problem both practically and theoretically. And intuitively, we think that, okay, if you find a more effective polymer, that means that you are increasing a parameter called Weissenberg number, you'll get higher level drag reduction. But the reality is slightly more complex. First of all, there's a threshold, a critical level of a Weissenberg number upon which you will see drag reduction. This is called onset of drag reduction. After that, you will see a steady increase of the level of drag reduction with Weissenberg number. But eventually, you'll hit another limit, another plateau, which is the highest level drag reduction you can achieve using polymer at a given Reynolds number. We call this the maximum drag reduction. And before you hit this MDR limit, there are also transitions between two stages: low extent of drag reduction, LDR, and high extent of drag reduction, HDR. I'm not going to go to details here for LDR, HDR. You can go to a number of previous references here. And this is what we typically do in simulation, in which we fix a Reynolds number and we increase Weissenberg number. In experiments, we typically have to adjust Reynolds number and Weissenberg number simultaneously to keep them in proportion to each other. So you'll be sampling the space in this direction, but you'll basically see the exact same sequence of transitions. For the limited time I have here, I will spend a lot of time most of talking about the convergence to maximum drag reduction. Therefore, I'll spend a little bit more time to explain to you the maximum drag reduction phenomena. So we know that if you have polymer, again, if you look at this Prandtl von Karman plot, which is a flow rate versus Reynolds number, if you have a polymer, you are going to have a higher flow rate for a given Reynolds number. Therefore, the flow lines you are getting here will be higher than that of Newtonian turbulence, right? And how much higher will depend on what kind of polymers, what's the concentration, etc. you are using. The more effective is the polymer solution is, the steeper the slope will be, right? But interestingly, no matter which polymer you are using, no matter what's the concentration, no matter what's the molecular weight, they are bound by the exact same maximum drag reduction asymptote. It is universal to different polymer properties. So any theory that explains this MDR phenomena has to simultaneously address three questions. Number one is what I call the existence question, meaning that we know that polymers can suppress turbulence, but why is it not able to completely suppress turbulence and give you dynamic flow? That means that there must be some mechanism sustain turbulence at MDR, but what is that mechanism? That is question number one. Number two is a universality question. So for this MDR state, which should be a state of very strong polymer influence, why polymer properties do not seem to matter, right? And number three, any theory to be complete has to be quantitative. So the theory have to be able to predict what's the magnitude of the flow rate at the MDR, which is given by this well-known empirical formula of the work profile. Okay, because MDR is a state at which the level of drag reduction converges into highest level for given Reynolds number, it has been widely assumed that that indicates the underlying dynamics of the turbulent flow reach some sort of a ultimate flow state, which is no longer affected by polymers. And this assumption has been guiding MDR research for nearly half a century. And different theories only differ in terms of which state do they identify as the ultimate state. The latest candidate is a state called elasto-inertial turbulence. By name, you can tell that it is a kind of flow instability, a kind of a turbulence in which elasticity is at least partially responsible to drive the instability, right? And compared with the classical turbulence we are used to, in which inertia is the driving force for turbulence, whereas elasticity is suppression-seen turbulence to give you drag reduction. These are two different kinds of turbulence. They are entirely different in their flow structures. So in inertia-driven turbulence, we know that the vortices always tend to align with the flow, whereas in EIT, we know that the vortices align in the span-wise direction. So they are very easy to tell apart. And more recently, we also came to learn that EIT is fundamentally a two-dimensional flow instability, which can be captured by an entirely two-dimensional direct numerical simulation. So the hypothesis goes that at MDR, any kind of 3D structure which came from IDT would go away, and you'll converge to this clean copy of two-dimensional instability called EIT. The problem with this picture is that EIT, because EIT is a state of high elasticity, it is really hard to explain why this state does not seem to be affected by polymer properties. So in this study, we use a direct numerical simulation of a channel flow, pressure-driven channel flow. We couple the Navier-Stokes equation with the Philippi constitutive equation, which solve for a tensor field polymer conformation tensor alpha, which basically tell you how much polymers have been stretched and what's the direction of its orientation. The coupled system will have 4 non-dimensional parameters, and for the purpose of understanding this talk, you only need to look at remember the last one, Weissenberg number, which is the product between the polymer relaxation time and the characteristic shear rate of the flow. So higher Weiss number means that your polymer is more effective to increase the elasticity of the fluid. It's more effective of affecting the flow film. So as said, we can find a 2D EIT solution. So the first step we take will be just to quickly check the hypothesis. If MDR is this 2D EIT state, then this 2D EIT state should be insensitive to increasing Weiss number and actually any polymer properties for that matter. So we find the 2D EIT state for different Weiss number. So clearly it is dependent on Weiss number, and it is even increasing with Weiss number. That means that you are not getting drag reduction, you are getting drag increasement or drag enhancement. Also, that for other polymer-related parameters, the 2D EIT is also clearly sensitive to the other parameters. So we may now conclude that there's no way that the MDR state is this simple 2D EIT state. But if we allow the simulation to run in 3D, allows flow in 3D, we can find that we are getting drag reduction for sure. So we are getting lower friction drag with the increasing Weiss number, but eventually it also goes to a plateau. So we do capture this asymptotic convergence to MDR as what happens in experiments. So on the left here is exactly the same graph, but I'm just adding more points here, and which is friction drag as a function of a Weiss number. And you can clearly see that we capture all the stages of transition see in experiments. So we have the onset of drag reduction, we have LDR, we actually have HDR, then the convergence to a final state called MDR. And also, interestingly, you may also notice there's this weird dip here. This is not some sort of artifact. What happens here is that as we increase Weiss number, once we hit Weiss number equals about 30, we cannot get a turbulent flow anymore. The flow will become laminar. But as we further increase Weiss number to 40, a new type of turbulence will emerge. So there's a laminar window that separates two regimes of turbulence. This is exactly what was observed in recent experiments by the Hoff group, in which if you increase the polymer concentration at a fixed Reynolds number, you will get into turbulence, then laminar, then turbulent once again. So this kind of separation indicates that there are at least 2 different mechanisms for turbulence. The second presumably is related with EIT. So we're looking into this point, which is basically right after the laminar window. Look at its dynamics in more details to look at what is the sustaining turbulence there. So showing here is just exactly the Weissenberg number equals 40 point I highlighted in the previous slide. So if you look at the dynamics showing in this colorful solid line here, it undergoes 2 types of cycles. One is small cycle. So you will go visit this so-called active turbulence, which is a state that is dominant in Newtonian turbulence. But you will escape active turbulence and go to the region that is closer to edge state, which is on the laminar turbulent boundary, and come back. So this type A cycle was previously known as active hibernating bursting cycle that has been reported for about 1 year up to now. What we find new here is the type B cycles, which is coexisting in the same space here. So in type B cycle, your flow will escape the active turbulence, and it will go to the direction of EIT, but it doesn't really quite get there. It will bounce back, then go through edge state and hibernation and come back to active turbulence. And if we further increase Weissen number, we can see that even type B cycle will go away. Both type B A and type B would go away, and we converged into another type, which we term type C cycle. It fluctuates in much smaller region of the domain. So let's take a closer look at these three types of cycles in the time series. I want you to look at the green lines here, which is basically instantaneous level of friction factor as a function of time. You see a lot of spikes on this green line. That's the spikes correspond to states of high turbulence, high drag, and we call them active turbulence. Between the spikes, you have these kind of dips. There are two types of dips. The shallow ones last for a few hundred time units. These are the hibernating turbulence, hibernation. And these cycles are basically the type A cycle. The deep dips here can last up to 1,000 time units. And within these dips, elasticity become partially responsible for driving turbulence. We call them type B cycle. So if we increase Weissen number to 64 here, we can see that type A cycles go away, type B cycles become much longer, and they become dominant. And if we further increase Weissen number, go to 400 here, we can see that both type A and type B go away, and we end up with a new kind of cycle which show up as a quasi-periodic wiggles, and these kind of wiggles we call them type C cycles. So let's look at the transition as we increase Weissen number. Right? So again, we listed the phenomenological transition from onset to LDR to MDR. Now we look at different dynamics here. Type A covers all the way up to part of the HDR. Then we have a laminar window. We have coexistence between type A and type B. Then we have type B and type C, and it actually goes to much higher Weissen number. Interestingly, for the regime that corresponds to MDR here, it is at least covered by two different type of dynamics, type B and type C. So it is no longer one unique ultimate state. If we further look further into the type C cycles, so here we just show the time correlation functions in type C cycles with increasing Weissen number, you can see that the fluctuations are getting higher, and the periods, the frequency gets lower, periods gets longer as we increase Weissen number. So that means that even in type C cycle, it is not one type C cycle, but it keeps on changing with polymer properties. So what we observe here that behind the convergent drag reduction flow rate in MDR, the underlying dynamics never really converge to a constant level. Constant state. There are at least two different classes, and with the increasing Weissen number, the characteristics of the fluctuation keep on changing. One thing I want to touch upon very briefly at the end is that so far we have been talking about EIT as part of a type B or maybe type C cycle, which occur at a high Weissen number. Actually, EIT-like structure will also show up as part of the flow domain in IDT at a much lower Weissen number. For example, this moment of active turbulence in which we can see those kind of span-wise riblets near the wall. These are EIT-like structures. We can confirm that by looking at the rate of energy conversion from elastic energy to turbulent kinetic energy. So we can see that there's a small positive peak near the wall here at a Weissen number as low as 16. So we do have this EIT-like structure that is coexisting with IDT spatially in the domain at a much lower Weissen number in type A cycle. It's just that they were not dominant back at that level. So to conclude, we report with increasing Weissen number, we record the transition from type A to type B to type C, three different cycles. Type A cycles is a well-known active hibernating turbulence cycles in which EIT can show up intermittently as part of a domain which coexists spatially with IDT. In type B cycle, EIT become one link in the cycle, so that if you remove EIT, you cannot sustain turbulence anymore. In type C, you basically converging a new kind of quasi-periodic dynamics in which EIT also plays an important role. one important take-home message here is that behind the convergent drag reduction in MDR, the underlying dynamics is not convergent to any ultimate state. It actually keep on changing. It covers two types of dynamics, and the frequency and the fluctuation magnitude keep on changing with the increasing Weiss number. With that, I'll conclude here. Thank you.